All right, welcome back. So I got a couple of really good questions during the break. Can you hear me? Okay. Okay. One question was, so what is actually an aerosol? That's a really good question. And apologies, I should have put out the definition right at the beginning. Sometimes I do this, but I didn't this time. So an aerosol, it's actually interesting. It's not just the particles, right? An aerosol is a collection of particles suspended in a fluid. For us, the fluid is air. And it's a collection of liquid or solid particles. And it could be a wide range of sizes, shapes, and compositions, right? So that's part of the complexity, but also part of the simplicity, right? So aerosols, this is an example of an aerosol. And the size ranges, so that's a little bit by convention, right? So these are the typical size ranges that we consider. This doesn't mean that there are no particles in the air that are maybe even a little bigger, but they would fall out really quickly, right? So for our intents of purposes, this is the relevant size range, from 10 nanometer to a few tens of microns. Pretty big size range. Okay, so that was a really good question. So thank you for that. And then you had another question? Yeah.
These log normal distributions seem very ubiquitous in aerosols.
Yes.
Is it because of the growth mechanism or because of how we sample them towards these logarithmic things?
That's a really good question. And I think there are a couple of papers that try to explain why is the log normal, why is it always log normal? And I think you can show if you make aerosols mechanically by making things finer and finer, eventually you will get a log normal. That's part of the reasons. However, there are particles in here that are not made by mechanical making things finer and finer. And then it's much more actually surprising that they still look log normal, but they do. Yeah, they really do. This is an idealized figure too. So if you go out for measurements, it might not fit that closely, but it's surprising. It's quite astonishing how good a log normal fits. Any other questions about this graph? Yes?
Plot on, you showed two pictures about clean clouds and polluted clouds. Is it visually, can we actually see that whether it is a polluted cloud or a clean cloud? I've seen a lot of fluffy cumulus clouds, white clouds in Tennessee. Mm-hmm. Back home, also I have seen white clouds. Here it is more reflective than the other one. So can we say it is polluted?
I think it's very hard to do this with just looking at it with the eye. Mm-hmm. Yeah. Any other questions? Anything you always wanted to ask about aerosols and never dared to? Yes?
With the polluted clouds, when they do rain, does that distribute the pollution on the ground?
Yes! And that's part of the acid rain problem, right? And also how aerosols get removed from the atmosphere. Why they don't, you might wonder, why don't we have all these emissions? Why don't they accumulate and get more and more and more? Because one of the removal mechanisms is raining out. And so the aerosol that was the nucleus gets removed. We call this wet scavenging. Mm-hmm. All right. Now it's your turn. You have to do something. Okay. Size distributions, okay? So we can look at number distributions, volume distributions, and one can also look at surface distributions, right? How the surface is distributed with size. So I want to know from you, this is all the same aerosol. One time it's plotted as a number distribution. One time is it plotted as a surface distribution. And then the third variant is the volume distribution. So which one is which? So you can talk to your neighbor.
Number should be A.
Uh-huh. Yeah. So we have one guess here. Number should be A.
It scales with the
All right. Why do you think this?
like the number will scale with the I don't know what that means. Like this, so you have like number distribution, they will be shifted, like length distribution, then surface distribution, and volume distribution, like that.
Oh, you mean
But now when I think of it,
yeah.
no,
I think you're right.
this might be. I think this number. I think B might be.
Volume distribution. Is it the total contribution of all the aerosols in that diameter? Or
Yes.
the total contribution of all the
Yeah. In that diameter.
That doesn't matter. That doesn't matter. Because like your sample is very skewed depending on where you are. But like if you take it, it's like
What did you agree on?
I would say also has the highest volume and the same
All right. Looks like you correct it.
Represent like,
You want to explain it to us?
Actually, wait, no.
like for the same mass,
No, yeah.
What's your name, Sergio? Okay, Sergio is going to explain it to us. Right, there we go. Yeah. Smaller, yeah. Yeah. Okay. So this is from a textbook. By the way, if you ever want to read a textbook on aerosols, I highly recommend a book called Seinfeld, by Seinfeld and Pandis. And I think the latest edition is from 2016. Don't quote me on the title, but if you Google for this is like, I use it almost every day, literally. And so yeah, this is how they stack up, right? It's the same population, but plotted in different ways. You explain to me the number distribution. The small ones show up as most frequently. And then how do we get the surface distribution? Well, we take whatever is in each size bin, and we multiply it by something proportional to d squared. And then we get this middle picture, right? So the medium-sized one now contribute the biggest amount to the surface. And then the volume, now the big guys show up, right? Because it goes with d cubed, d to the power of 3. Yeah. That's how that works. So now we know about number distribution, surface distribution, volume distribution. Check out the units, right? Okay, so let's go on here. We already talked about the modes of a distribution, distinct ranges where a peak occurs, and this has to do with how the aerosols are brought into the atmosphere, right? So they basically reflect the way they were made, and we will talk about this in a little while a bit more. Okay, so there's another way this is not the only way, right? So size distributions are a good way to characterize the state of the atmosphere, but sometimes, especially in air quality, we don't really worry about so much what exactly the distribution is, right? We just worry about the aggregate of how much there is, what the concentration is, the mass concentration of particles smaller than a certain threshold. And so the two important thresholds are 2.5 micron. And so everything smaller than 2.5 is called PM 2.5. And then everything smaller than 10 micron is called PM10, right? So, this would be the cutoff here. And of course, this glosses over all this detail, right? We have a huge amount of these particles and less of those. So we just count them all together in terms of a total mass. And so the reason why these two sizes are chosen, or we have names for them, is the EPA has standards for them, right? So PM2.5, there are standards, and we can't exceed them. And so that's what's going to be monitored. We have stations that measure PM2.5, and they don't worry about the size distribution, right? They just look at total mass. So that's how that relates to the size distribution. So bulk quantities, we just choose a cutoff, and then we count everything, and we weigh it literally, and that's the number that we track. Okay, more for you to do. This is a little bit more complicated. Let's see how this goes. There are instruments. So now we looked at totals, right? So this here was a total volume distribution. But it didn't tell us from this plot what the actual chemical species were that make this up, right? It could be all dust, or maybe it's all soot. Probably not, because soot doesn't make such big particles, right? Or maybe it's a mixture, right? This is your dust, and here is your sulfate and soot mixture, could be. So there are instruments that measure this at least up to a certain size range. It's actually really hard to measure these very big particles because it's hard to get them through the orifice of the instrument, et cetera, So this particular instrument is called an aerosol mass spectrometer, an AMS. Has anyone heard of AMSs? No? And it really revolutionized our field of atmospheric chemistry, because what happens is you can deploy it, and it used to be, to get the composition, you have to take a filter sample, and you have to take it to the lab, and you have to analyze it. So an offline method, right? Which is always, implies there is a time delay. With this instrument, you can do it online. So they suck the aerosols through the instrument, and as it's going, it's analyzing it, and it's figuring out, it's measuring how much of these different types of aerosol species are in there. And so the way it cannot measure soot, sadly, because it can only measure things that evaporate, right? So it gets basically heated up until the species evaporate. So some organics do that, sulfate, nitrate, and ammonium. And then that's what it analyzes. And so that's the reason why it cannot detect dust or soot or actually sea salt. But it can do at least organic sulfate, nitrate, ammonium. And so in this one paper, they measured the aerosol population in different periods. They found out the total mass concentration is this 106.5 microgram per cubic meter. And these are the mass distributions of the individual species, right? So there is some organic, some nitrate is the blue, some ammonium, and some sulfate. And that's the distribution. Okay, makes sense?
AMS, is it aerosol mass
Spectrometer, yeah. So AMS, aerosol mass spectrometer. Yeah, and so this really has, what I wanted to say was really an important thing for our field, because now you can deploy this instrument in different locations, and you get a very good timely resolved and size resolved, right? Not just the total, you get also a size resolution. You know where do you have most of the organics, in which size range, and so on. From many different areas around the world. So we now know so much more because of this instrument. Okay, what I want you to do is, do you have something to write? Okay. I want you to pretend, so this is a distribution, right? And so by the time we look at the distribution, we almost have forgotten about that there are actually individual particles. So I want you to remember this distribution is actually comes about by looking at individual particles, okay? And so I want you to pick 10 particles from this sample. And you could pick it from where you have most, right? From this, where the peak is, or wherever you want. And then I want you to draw these particles. What are they composed of, right? So we know, for example, at this size, this is the total, but there's organic, sulfate, ammonium, and nitrate in there. If you sample 10 individual particles, what do they look like? Do you understand what you have to do? So just, not the molecule, just kind of like a pie chart, right? Let's say each particle is a pie chart. We have 10, 1, 2, and I'm picking this size here, this size range. So I'm making them all about the same size. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then what I want you to think about is what species goes where. Like, is this the first one? Is this maybe? I try to lead you towards this idea about mixtures, right? And how to distribute the species over the population. So take a couple of minutes and then we will compare. And the result is not in there.
Should have a size distribution.
Well, these are particles, right?
Yeah.
And we size them, and we know now the mass distribution.
Yeah.
So now, what were the particles that actually made up this size distribution?
Okay.
You didn't understand? Okay. So this figure, right? It tells us what the distribution is of different masses, right? But it came about because you sampled lots of particles, right? So if you pick a certain size, the one I marked there, you see most of the material is actually organics, right?
Yeah.
And then the second most abundant is sulfate. And then we have about the same amount of nitrate and ammonium, right?
So if you compare organic with sulfate, organic has a more size than the sulfate, is it?
No. Organic has at that size more. That you have more organics, right?
Yeah.
Microgram per cubic meter. So this tells you something about the ratio, right? And so then, if you have these 10 particles, like what are they made of?
Which one are organic, which one are sulfate?
Yeah,
Okay.
yeah. And is there a unique answer? No, there isn't.
Because it is a ratio.
We don't know, right? Like this instrument.
It gives you a ratio, but not the actual.
Yes. Yes. Huh?
But what are they doing?
I don't know.
I only have one color.
Yeah, you have to imagine it.
I'll do it with dots.
Yes, you can do the black and white version. Whoops, sorry. Drop my.
I looked it up, and let me find it.
Oh, okay. You're
So
saying
according
here.
to Google, it made it.
Oh,
10
it did make it.
kilometers up,
Yeah.
and It took 15 days to Is that the time scale that you would expect
Yeah,
to see for stratosphere penetration? But it doesn't seem like it had that much of an effect.
Yeah,
on
maybe it wasn't just that much overall.
Okay, interesting.
It does sound a lot, but it's maybe not in one of these huge events that you need.
I thought it was a pretty substantial event. Maybe not that big, but because the mountain is.
Yeah. How are your particles going?
I think we're going well. I don't have any colors either.
Because it was pretty, mountain looks pretty much gone.
Yes, mountain's gone. Yes. Okay. You are very quiet.
It's going to be hard to like actually quantify.
Do you have something?
What we have.
Whatever.
And so they are made of a pure substance?
So that's also another because I realize it's microgram stuff, but I don't know organics.
Okay.
CHO.
All right. All right, so you have some organics, some sulfate, some ammonium. Okay. Very nice. All right, shall we, and you have a pie chart?
This was just in the end to just check.
Okay, okay. And you have mixtures.
Yeah, one question is like how we consume there's like particles that are composed of different items, like soluble organic compounds, like inorganics, organics, or like different particles that we use to put them together.
That's the question. We don't know. So you got what the exercise is about, right? So the exercise, I do this with my students before they get indoctrinated by me. And that's what you should have something like this, right? So some of you thought, okay, I have my organics, my sulfate, my nitrate, my ammonium, and it's separate, right? And others, you were thinking like this. Each particle is a mixture, and it contains some of each, right? Could be. Some were thinking a lot about shape, so this is not so much about the shape now. This is more about composition. And yeah, and so that's the point of this exercise. From this measurement, we don't know. It's not unique, right? You can have many, many different populations of different compositions that give you the same mass distribution as it's pictured here. Make sense? And I see you were struggling with how should I make all of them organic, or should they be mixtures, and what kind of mixtures? That's exactly the conundrum that we have in aerosol science. And so, to my knowledge, this was articulated for the first time by Winkler in 1973. And so let's read the sentence together. The same net composition of an aerosol can be caused by an infinite variety of different internal distributions of the various compounds. And so this is what we call the aerosol mixing state, right? So you can have the same, these are 6 different aerosol populations that have the same, what we call bulk composition, right? It's half red, one third yellow, and 1/6 blue. But you can take that material and you can distribute it in different ways. So we call the left thing an external mixture. And the right population we call an internal. And so the internal mixture, that composition, each particle basically resembles the bulk. If you know the bulk composition, you know the composition of each particle. Versus the other mixtures, the external mixture doesn't, right? Each particle is its own unique species. And then what do you think the real aerosol, like is it this or this? Or what is it? Is it this? Who other opinions? It depends, right? And I tell you, it's rarely this or this, actually. These are idealized. As a modeler, we really love this. This makes things very easy. Or even this. But in reality, it's often something in between. And this is just one example, right? So you can find as he says, infinite varieties, how you can be in between those states. And what is my next slide here? Okay, wait. I thought I should have this slide here. It actually matters, right? So the impacts that we talked about, let's say becoming a cloud droplet, right? For that sort of process, it really matters what the particle is made of, because the way they take up water, it depends on the chemical composition, right? We already established soot is not so good, and something like sulfate or sodium chloride is really good at taking up water. So you know this from your kitchen, right? And if you have like salt in this kind of weather, it draws in the moisture. So that's exactly how it works in the atmosphere as well. And let's say, for example, the red is soot. So these were little soot particles. And then we have an organic, and this one is a sulfate, right? Let's pretend that's how it works out. So maybe in this condition, and we try to make a little cloud. And by the way, how do we make clouds? we lift up. We have to cool, right? We have to bring the parcel to saturation. And in the atmosphere, this works by, for example, by lifting up the parcel. So we lift up our parcel. And then in this condition, maybe only we get one cloud droplet, because only the sulfate is really nice hygroscopic, and the other 5 don't make it, right? So we get only one cloud droplet, and that cloud droplet would grow very readily and make a big drop that eventually rains. And compare this to this one. Here, our soot is together with sulfate and organic. And so this little bit of sulfate can help the soot to actually become a cloud droplet. Suddenly you have six times as much than here, right, in the first case. And so this cloud will look very different to that cloud. And so this is why the mixing state really matters for the cloud microphysics. So this would be now an example for the cloud microphysics, but you can make similar examples for scattering of radiation, right? Scattering and absorption of radiation. So if you have a soot particle, it doesn't actually look that spherical, right? You have your soot particle, and here's another soot particle that is covered with something non-absorbing, and here the non-absorbing is separate. This is your sulfate. Sulfate, soot, and here's a mixture of soot coated with sulfate. It turns out that this soot coated with sulfate actually absorbs more radiation per mass of soot compared to the bare soot, because they call it the lensing effect. So the non-absorbing material that is around the soot is lensing the radiation. So this soot sees more radiation than that one, and so it absorbs more. So also for optical properties, this mixing state matters. So mixing states. For cloud formation and cloud properties, right? And also for optical properties. So if we are interested in climate, both of these things are basically at the bottom of the aerosol climate impact. it's also, if climate is one big thing why we care about aerosols, but then the health impact is another one, right? And so if you think about how deeply it's all about how deeply can these particles penetrate into the lungs. And so what happens is when you inhale a particle in your airways, it's exposed to a higher relative humidity, right? So the particles will, if they are hygroscopic, they take up water, they grow, and then once they are a little bit bigger, they can't get around the curves in your, what do you call this, your airways, basically, and they get stuck, right, which is good, because we want them to get stuck. We don't want them to penetrate really deep into the lungs and then get into the bloodstream. So the fact if your soot particle has a coating or not can really determine where it gets deposited in your airways, in your lungs. So that would be a health impact example why mixing state matters. Okay? All right, so now you know what aerosol mixing state is. You know why it's potentially, or why it is important, why these details matter, and why a size distribution or a mass, even if you know the size resolved mass, that's not actually enough to characterize an aerosol. So how should we really, what's the right way to think about an aerosol? And so I think this is the way, if you take away one thing from this session, this is it, right? It's about the composition space. And so let's look at this, right? Now that we know a little bit more about how aerosols, what they can all contain and so on, let's think about this. Let's pretend now we only have three species. A black carbon, this is your soot, some sulfate, and some organic. And in reality, of course, there are many more, and the organics are actually so many different individual species, but we now lump this into this three component system because it's easier to draw, right? We cannot draw very easily in 20 dimensions. Okay, so the way we think about this is each particle is actually a vector that contains a certain amount of each of our species, right? So for example, particle 1, which is the red one here, contains a bit of, so these are just relative units, a bit of black carbon, a lot of sulfate, and some organic carbon. And then particle 2 is here, and particle 3 similarly. So that's pretty straightforward, right? And so now, in a moment, we will talk about processes that change this, right? For example, you can have condensation of sulfate onto this population of particles, and what would happen is that all three of them will move in this direction, right? Because the sulfate amount increases. Or you can have the process of coagulation where particles meet each other. For example, particle 2 and 3 meets. What you do is you add up those components, and your new particle, you basically delete the 2 and 3, and you make a new one, and it sits wherever you get when you sum up your components, right? So that's really what aerosols are. So they occupy this composition space, and that's what we have to deal with when we want to model them, right? Okay, and so in reality, the composition space is, of course, much higher. So typically in a model, we will have maybe 20 different aerosol species, a few inorganics, and then the organics. There are lots of them, which is a challenge in itself. So it's a 20-dimensional space in that case where this cloud sits. And then now you think, oh, what about the size distribution? How does that relate, right? So you can think of the size distribution as a low-dimensional projection of this composition space, right? So from the masses, let's think about this as mass units of a material in your particle. You can add this up, get the total mass. If you know the densities, you get the total volume. If you assume they are spherical, you can get the diameter, right? And so then once you've done this sort of like projection, you can draw it as a size distribution. But of course, you lost all that detail about the composition space, right? So because now it's just a one-dimensional distribution, and here it was a however many species you have in your system, dimensional distribution. Okay, are you still with me? Okay, good. So now, after having established this, let's look what models do, right? Which is, if for my experimentalist friends, it's always a big shock. What do models do? And just to tell you, there are different types of models, right? And they get used in different ways, and depending on what your question is, the different types, the different structure, one structure is more appropriate than the other. So these are the main types, and as a reminder, this is what it really looks like, and then you can see, and you can judge yourself how terrible this is. The simplest type are bulk models, and so this means we don't worry about sizes, we just count up the different species in terms of mass, right? So I go here with species A, B, C, it doesn't matter. We might have more than that, but we have a certain amount of A, a certain amount of B, a certain amount of C, and so this would be essentially microgram per cubic meter, and this is what you track in your model, right? So your aerosol state is described by 3 numbers, and that's your total concentration. It's very similar to the gas phase, right, where you just have the concentration of the gas phase species. Here you have the concentration of the aerosol species in the aerosol phase. But now you already know, oh my God, but there's all these different sizes, and what about the sizes, and who is together with who, right? This gets completely shoved under the rug with this approach. But it's computationally, of course, very efficient because we only have very few state variables comparatively. Then the next big type is the models that actually take size into account, because size is so important, right, for cloud formation, for optical properties. So people who do aerosol modeling for atmospheric aerosol realize this very, very quickly. Okay, we really should get the size involved. And so then what they do, they also realized, oh, log normals fit really well. So let's just represent the overall size distribution with these different modes. And each mode can have certain species. But within each mode, we don't know really, like just this exercise that you just did, we don't know how the particles really look like. We have to make assumptions. But that's what we do. And then another similar approach is not using modes, but using sections, right? Again, we know the average composition per section, but we don't really know what the particles look like when we pick a certain section. And then the most computationally intensive approach is a particle-resolved approach, which is what we've been working with a lot, where we don't have modes or sections, but we throw a whole bunch of computational particles on our population, and we sample our real population with those computational particles. And then we are less restricted, right? So we can resolve the mixing state better, but you can see there's still a lot of abstraction, right? So we normally assume particles are spheres. We don't really are very good with tracking what's in the middle, how are the different species arranged, right? That kind of thing. They look like little pie charts, and I did this intentionally because we are agnostic to, does it look like this or like this complete coding? Yeah, but at least in terms of mixing state, that would be the most detailed way, and the bulk models the less detailed way. Okay, so different types of models that track different aspects of the aerosol state. Check, check. And so the model assumptions, depending on what you choose, you have different model assumptions. And you also have different state variables, and you will need different types. You have to prepare your input data, And the way you compare your data to real data in the atmosphere will differ depending on what you choose for your representation. Okay, and so this is, I already said this, as we go from left to right, it's getting more accurate, more computationally expensive, and you can resolve this mixing state more and more. Okay, so another, because this is when things get modeled quite a bit. The difference between prognostic quantities and diagnostic quantities. So prognostic quantities are the things that are directly predicted by models, and which variables these are, that depends on the structure of the model, right? So a bulk model will have different prognostic variables than a particle resolved model, as opposed to diagnostic quantities. These are the quantities that we don't have like a prognostic equation, a governing equation, but they are diagnosed based on what your model tells you, right? And oftentimes this requires additional assumptions or more like another physical framework or chemical calculation framework to figure this out. And so I want you to think about, from this list of variables, which ones are prognostic variables and which ones are diagnostic variables, based on what we said so far. And talk to your neighbor and think for two minutes or so, and then we will compare.
Look at them, maybe 1 or 2 minutes.
What is the actual shape? I think like I don't think this is that's why you're probably very.
And if you don't know about a term, just don't worry about it.
Aerosol optical.
Basically, basically,
I always know the optical.
It's just like, over time they see how it shapes out. That's why I have like
but I don't think it will be accurate, so I would think it's a diagnostic one.
I'm not sure what it is.
I think you can get that out by prognostic.
Prognostic or diagnostic aerosol. This is like
I'll trust you.
Again, I went 0 for 3 on the last one, so.
I know.
I think it's like speciation. No, I think it's like condensation. It's not experimental. Yeah.
Well,
I think this could be
Yeah, I think this is like.
but you'd have to know the shape, like the amount of things.
That's
Number concentration prevents.
yeah, that is prognostic.
Extinction. What is the extinction called?
I'm not exactly sure what the extinction is. That is something.
Because for each individual one, aerosol, I assume you can diagnose.
Because I have PhD for a while.
The rest of them,
So that we don't.
Yes. Well, it could
So that
be,
we
I mean, depends, right? I don't think we have time to really explain that, but depending on size and composition, it could be more or less Yes, yes.
This is question mark. What is the extinction code?
Especially for the small subparticles, it's very unrealistic.
It's an optical property, how much light it extinguishes. Yeah.
Like whatever original
Yeah. We need an optical model to figure that out. Yeah.
No, I would say
Yeah.
Why just go over physics and
Probably.
I'm feeling
Sorry.
I'm feeling restless right now.
Did you go to the gym?
No, I didn't go to the gym. I did wake up at 5. So I thought about it for a short
What have you got for aerosol optical depth? Diagnostic. Do you know what that is? It's basically the extinction coefficient integrated over. It's something to do with the optical, how much light it extinguishes, right? And it's a measure of how much aerosol you have, but the model can't predict it directly, right? We have to know how much aerosol we have, and then we calculate it. So that's diagnostic. What about radiative forcing? That's the slide I showed at the beginning.
Same thing, diagnostic.
Diagnostic, yeah. Lots of, it's quite removed, right? It takes a lot to diagnose, actually, from the aerosol loading. Cloud condensation, nuclei concentration.
Say prognostic.
Diagnostic. So it's diagnosed based on the aerosol population, right? And then we need to throw in a model that tells us if this is the composition and the size and the supersaturation is that, can you become a cloud condensation nucleus or not? So also diagnostic. Number concentration per bin. Prognostic, yeah. Extinction coefficient, another optical. What? Diagnostic. Yeah. Again, this is something we would calculate based on what the aerosols are, and how many we have, what their size is, what their composition is, and then there's optical. We need to do some optical calculations, like calculations, in case you have done that before, and then we would get how much it extinguishes. Species mass concentration per mode. Prognostic. Yeah, this is. If you have one of these models, right, a modal model, the mass concentration is actually, in these modes, is actually one of their prognostic variables. Okay, now maybe you have a little bit of a better idea what these models, what are the state variables, and what are we actually predicting, and then what are we deriving based on that, right? Okay, and so here I've written it out. Again, bulk models, mass concentration, MA, BC. For a modal model, in each mode, we have a prognostic equation for the number concentration and then for the mass concentration of our species in the mode. And similar bin model and then particle resolved model has many state variables, right? For each particle, essentially, how much does it contain of our species? And then you go down the list and you might have thousands of particles. Okay. Let's see here. Okay, and so now again, really to hammer home this idea, we have the high dimensional composition space, which a particle resolved model gets to. And then these other models, they are projections in certain ways, right? And we can always go from here to here. But when we are here, we cannot go back uniquely. That's the crux of it. If we have such a model, a modal model, for example, we can't go back and figure out what do the particles. This is what you tried essentially to do with this figure, right? And you saw how tricky it was. There is no unique answer. Okay, good. All right, little summary. What is the aerosol state? Aerosol state is a distribution of particles in composition space, and it describes what aerosols are physically and chemically at a given time and location in the atmosphere. And then different models have different ways to represent this aerosol state, and we talked about these 4 different categories. And then you have this trade-off between accuracy and computational costs. Choosing the right level of detail depends on the question and the resources you have, okay? And so just to maybe help you to see where this is going. So in these 3D chemical transport models, and it could be like a global climate model, or it could be a model that works on shorter time scales where we just want to know the air quality on a global scale. We have a computational grid, right? So you have this for your combustion applications too. You have a computational grid in your engine, for example, right? So we do the same thing. We put a computational grid on the globe, and then we have transport between layers in the vertical, and then between columns, right, in the vertical and in the horizontal. So that's your Navier-Stokes equations that we need to solve. They tell us how things are moving in the atmosphere. And also the turbulent diffusion, right? Like how turbulence is mixing things around. So that's the transport. And then in each grid box, we have a model for the gas phase and the aerosol chemistry and dynamics, right? That predicts what the aerosols and the gas phase species are doing. And this is how we move ourselves forward in time if we want to figure out what happens 100 years from now, right, with a different climate. So this is what we have to do. Okay, so that's good timing. We are almost at the end of the second hour, right? How did this go so quickly, at least for me? So next thing what we want to talk about is actually the processes, right? So we spend a lot of time, what is the aerosol? How can we describe it? But the transformations are really key, really understanding what's all going on. And so I'd like to cast this in this way to talk about the life cycle, right? So there's the birth, how get new particles being formed in the atmosphere. There are two ways how this can happen. Then there are many different ways of transformation. So we will talk about a couple of those. And then how are they removed, right, from the atmosphere? Yeah, so in those sections. And we do a little bit today and then some more tomorrow. And our goal is to develop an equation that describes how our aerosol state changes in the atmosphere as we move forward in time and as a function of space. All right, I'll say we have a break now again and then reconvene in about